It's a
Our
very
Vice
great
President.
pleasure to introduce Dr. Amy Simon, our speaker tonight, and also her husband Steve and son Sean. Amy obtained her Bachelor of Science in Space Sciences from the Florida Institute of Technology, and very impressively, while still an undergraduate, she was already participating in research. Her master's and PhD in astronomy was from New Mexico University, where her mentor and thesis advisor was Dr. Rita Beebe. Her research at New Mexico State was on the atmospheric dynamics of Jupiter, including its weather, and also its chemistry and the effects of the impacts of comet Shoemaker-Levy 9. Very admirably, prior to her thesis, she already had 7 publications. She did a postdoc at Cornell and then joined NASA Goddard. Her work on all 4 of the giant planets used data from Hubble, Voyager, Cassini, Galileo, and New Horizons, and also ground-based telescopes. And she's currently on the mission teams for OSIRIS, Rex, and Lucy. Since you're probably much less familiar excuse me, with those 2 missions, I'll just briefly say something about them. OSIRIS-REx is designed to scoop up material from the surface of the asteroid Bennu and then return that material to Earth. That's quite astounding, really path-breaking. We'll really be eager when that material comes back and can be analyzed. Lucy is another spacecraft to study asteroids up close, and it should launch next year. It's going to visit an asteroid in the inner part of the asteroid belt, but most importantly, it's going to be visiting Jupiter's Trojans, the 2 groups of satellites that are 60 degrees ahead of Jupiter and 60 degrees behind Jupiter in Jupiter's orbit. Those are, the Earth has Trojans too. Any sufficiently massive body will. But those are points of where something can orbit stably. So fragments from the early collisions, the collisions in the early history of the formation of the planets and solar system are expected to be there. Dr. Simon is also the principal investigator of the Hubble Outer Planet Atmosphere Legacy Program, which observes all 4 of the giant planets every year. Today she'll be telling us about the ice giants, Uranus and Neptune, which are they're the last major planets before the Kuiper Belt begins. We know much less about those 2 planets. They're rather unusual, so we're eager to hear about them.
Thank you.
Thank you.
So thank you very much for having me tonight. As John just alluded to, I'll be talking to you tonight about the mysteries of the ice giants, because we know so little about them. And so to just jump right in, first of all, the images up on the screen there on the right are from Hubble last year, 2 years ago now, 2018. And you can tell already they look very different than what we saw from Voyager. We have another big dark spot actually in the north hemisphere of Neptune that we just discovered in 2018. And Uranus is actually looking quite different too. That polar cap's very bright. The hazes have gotten much more dense as the seasons have changed, and we can see some polar storms. So these planets already look quite different than what many of you probably remember from textbooks or from the Voyager flybys. And so what I'm going to talk about tonight is, first of all, ice giants versus gas giants. What is the difference between these 2 planets and Jupiter and Saturn? How are they different from them? How are they different from each other? Because they're really 2 different planets. They're not at all just the same thing. And then why they're so important in general to study. I'll talk a little bit about the observations that we've been taking over the years and the missions that have been there. So primarily what we've learned from Voyager and what we didn't learn, and what we've been doing in the meantime, particularly with Hubble and ground-based telescopes to learn more about them. And then I'll finish up with going forward. What is the future for these planets? When are we going to get there? What missions are potentially on the books? So So that's where I will end. So ice giants versus gas giants, why are they so different? And these, sorry the color's a little garish on the screen, but these are maps that we made from Hubble data as each of the planets rotated, and we essentially unwrapped them. So we rolled the planets out flat so you could see all the sides at the same time. And of course, Jupiter in the upper left there has the most structure. You see all of those clouds, you see the great red spot, it is still there. It's smaller, but it's still there. It's got a lot of color to it. Now, you guys all know, every image we put up is false color. It's not real. We take filtered images, approximately red, green, blue, and we make a color out of it. It's often exaggerated to bring out the details and because it makes for better press pictures. Sometimes for scientific reasons too. But, you know, obviously those are not the colors you see through the telescope. They're not the colors I see through the telescope. But those differences between them are real. So Jupiter does have much more of that burnt browny color to it. It's very beige to me through the telescope. You see a little bit of brown red on occasion. Saturn is that nice yellow. In this particular color composite, because it is very narrow band filters, it exaggerates the bands. So you can see Saturn has banded structure just like Jupiter, but much more muted. And then you get to Uranus and Neptune. And those are our nice pretty blue planets, right? Uranus, although it doesn't have a lot of cloud structure going on that you can see, there are small storms from time to time, but then it's kind of covered with more of a haze. So you're not seeing a lot of banding, you're not seeing a lot of big structure and storms. Neptune, on the other hand, is a very clear atmosphere. So we don't have a lot of haze, it tends to be a little bit of a deeper blue. You see the storms that pop up from time to time, but it's not quite as hazy looking as Uranus. So, you know, why do they each look different from each other? So first we should take a step back. What is an ice giant? When I was in school, there weren't ice giants. There were just giant planets. They were all the gas giants. So why did we start calling them ice giants? And this is because we really wanted to distinguish the fact that Uranus and Neptune are very much different than Jupiter and Saturn. They're not just smaller gas giants. Now, one misconception to clear up right away is gas giant. That doesn't mean it's just a big ball of gas. Okay? It's not. The gas giants have cores about the size of the Earth, so a fairly substantial core, and a huge envelope of molecular hydrogen. And this is why we call them gas giants, because they're primarily hydrogen. Now those clouds and hazes that you see on the top there, those are from very, very tiny little trace amounts in the atmosphere. So we have just a little bit of methane, just a little bit of ammonia, it freezes out, and you get that great cloudy top to the atmosphere. But that is a very, very small component of the atmosphere. So for those two planets, it's primarily hydrogen. For Uranus and Neptune, it isn't. So we have those same small cores in the middle, but above that is an envelope that's much icier. So we call it ice giants, but don't think it's a solid ice ball. It's still not. All four of these planets are probably slushy, right? They're fluid. There aren't hard layers in them, but it's a transition. So even when we talk molecular hydrogen versus metallic hydrogen, methane ice, water ice, we're not talking solid surfaces. So we're just talking about a transition from one material to the next. So Uranus and Neptune are primarily made up of these compounds that would freeze out. They're ices, methane, water, ammonia, and then they do have some hydrogen as well. So to distinguish the fact that they are very different from each other, some scientists started to call them ice giants. And many of us fought that for years, I will let you know, because we don't like change. But I think everybody's given up now. They really are very different, and so it helps us distinguish them to have gas giants and ice giants. But they are still those same four giant planets you all learned about. So what else is different about them? Well, of course, they have different tilts. So Jupiter has very little tilt, about 3 degrees. Saturn and Neptune are about 30 degrees, not too much different than the Earth. So you can imagine that they'd have seasonal change, about on par with that. Uranus is flipped all the way over on its side, a little bit past even, so we say 98 degrees because it seems to be rotating in the wrong way. We have no idea how you do that in the solar system, how you flip a planet on its side. And all of its moons are still in orbit around the equator like every other planet. So they had to have formed at the same time as whatever flipped it on its side. So already we have a big difference between those two ice giant planets. One is way over on its side, and you can imagine that really affects your seasons. because one pole is looking at the sun for seasons on end versus, a little bit of a hemisphere. So what does that do for how we see those clouds and hazes? What we know, and this is again not from direct measurements, it's from inference. We know what we think the clouds are on each of these planets. So for Jupiter, that top cloud you see, that whitish cloud and sometimes brown, orange, whichever color in your color composite, is ammonia ice. Now ammonia ice is white, but we get those colors probably from stuff that rains out in the atmosphere, and possibly from some of the next cloud layer, which is ammonium hydrosulfide, and that turns red. Saturn, on the other hand, has those same clouds, and it's yellow. Why is it yellow? Because those clouds are a little bit deeper down, and we're seeing through more of that haze. When we get to Uranus and Neptune, they're so much colder, you can't even see the water or the ammonia ice. You're now seeing methane ice and hydrogen sulfide ice. So now we're getting pretty exotic here with what we're seeing in those atmospheres. And there's probably other stuff higher up as well. So that's part of what you're seeing when you see this color difference, is you're seeing very different cloud layers and through different types of haze. So what else is different? It's a complicated diagram. And what this is showing is you have sunlight coming in to any of those planets. Part of it reflects off, bounces away. Part of it's absorbed by the atmosphere and eventually radiates off. Well, if you look at how much sunlight comes in, how much gets reflected off, and how warm the planet is, if there's any difference in that, it doesn't add up to 100, then the rest is internal heat coming from the inside. And so each of the planets get less sunlight as you go farther out, but they also have different amounts of heat that they radiate. And so if we look at what temperature each of those planets should be if they had no internal heat, it's the top line there. So Jupiter should be about 113 Kelvin, so different units, not Fahrenheit. Saturn should be 83, Uranus 60, Neptune 48. They should be colder the farther out you get. What we actually find out is Jupiter's a little bit too warm. It has internal heat coming out. Saturn's a little bit too warm. It has internal heat coming out. Uranus doesn't. We don't know. Neptune does. So again, we have this problem of why is Uranus different than Neptune? Nobody has an answer for that, but one of the current theories is that whatever knocked it over on its side also swirled up its inside, and a lot of the heat came out, and gee, it doesn't have any left. Now, this is hard to do. It's hard to get each of the planets in the right place at the right time to start with, but now you also need to knock it over and get rid of all its heat. So it's still a little bit of a mystery on why that seems to be a little different than we expect. But there's one other thing to think about here. How do we measure the temperatures on these planets? The best way to do that is to get measurements, first of all, of that reflected sunlight by looking at the fully lit side. Pretty easy to do. To get that heat, you want to look at the dark side. So you need a spacecraft. Well, we've had exactly one flyby of Uranus and one flyby of Neptune, in 1986 and 1989 by Voyager 2. So we have one measurement. So if that measurement was off for whatever reason, maybe the instrument's at calibration, or we happen to look at a funny time, something funny happened, we might not even have these numbers correct. So one of the things we'd love to do is find a way to measure those again and make sure that that really is the case, that Uranus doesn't seem to have this internal heat, because we may just have a bad measurement. In general, you don't want to rely on one measurement for anything and assume that it's right. So that's something we'd like to go back and do. So one thing that should happen when you look at this balance of internal energy versus sunlight is you should see a change in the winds. Here on Earth, sunlight drives a lot of the winds. That's not true on the outer planets. So Jupiter has a fairly complicated wind field. We'll have east and west, back and forth. It doesn't change much over time. It's very constant. And the winds are up to 100, 150 meters per second. If you look at Saturn, Saturns don't go east and west quite as much. They mostly go east. So one problem we've been trying to solve is, why is that? Well, this is all relative to the rotation rate of the planet. And one thing we found out with Saturn in particular is it's hard to measure its rotation rate. Jupiter, because it has the tilt and the way its magnetic field works, we get essentially a lighthouse effect. So we can measure the interior rotation of Jupiter very accurately. Saturn doesn't have that. It has a radiation field, but we don't think it's generated from the inside. And so we think that that rotation period might have been off by at least a little bit, a few minutes. And that would change this wind field slightly. So we would get a little bit more into the west. So we get out to Uranus and Neptune. Well, now they're much colder, and Uranus doesn't have this internal heat. It shouldn't have these big, strong winds. Well, they're even stronger than on Jupiter and Saturn. So it's telling us that we, first of all, don't understand how to generate winds very well, but also that it's not just a thermal effect. Part of it's the rotation of the planet. There's all these things that go on. So we have winds on Neptune that are 3 times bigger than Jupiter. So it's still a conundrum to understand how these planets work, but this alone should tell you Uranus and Neptune are not Jupiter and Saturn. They're really very, very different planets. So, you know, why do we care? Why are they important at all? Well, first of all, these 2 planets, as was said already, they're the least explored planets that we have in our solar system. We've only had that one flyby. And in reality, when we went back to Jupiter with Galileo, when we went to Saturn with Cassini, we found all sorts of new things we weren't expecting. In particular with modern instruments, Cassini, when we looked at some of the moons, Enceladus had these great water geysers. We think Europa might have an ocean. We don't know what's going on most of these moons and even the planets themselves for Uranus and Neptune because we've never really explored them. We think that there is a chance that there is some activity potentially on some of these moons, even though they are so cold. And so that's one thing we'd love to explore in a lot more detail. If you look at the different missions we've had, this kind of really drives it home. When you look at Jupiter, we started out with the Pioneers in the early 70s. Then we had Voyager 1 and 2. We had, I'm skipping a bunch in between, but we had New Horizons, Cassini, anything that's needed a gravity assist pretty much uses Jupiter. So it's had a lot of flybys, and then it's had dedicated missions. And so now it's had the Galileo mission, which lasted from 1995 to 2003, almost a decade, and then now the Juno mission, which is in orbit. So Jupiter is very well studied. Now, I'm a huge Jupiter fan. I'm always happy to go back and look some more. But compared to the others, it's really gotten more study. For Saturn, we had the Voyager 1 and 2 flybys, and already we were in formulation for Cassini. It was designed to be the next big mission after Galileo, and so it was in formulation in the 80s pretty much as soon as we finished those Voyager flybys. The Cassini mission, I think, was a resounding success. It was in orbit at Saturn for almost 2 decades, so we learned an awful lot about the Saturn system from that mission. Certainly well worth the cost. Uranus and Neptune, we've had that single Voyager 2 flyby, and it happened to be the alignment of the planets allowed us to do that with Voyager 2, so it made it easier. That's certainly true. They're very difficult to get to. They're far away. But we just don't have that body of study that we've had for the other planets. But the thing is, the ice giants really challenged our understanding of how planets formed. When we look at how you get a planet, it does take the right things in the right place at the right time, and we'll talk about that in a second. But when we try to make a picture that has all of our 4 giant planets in it, we've made models, and you know they require everything exactly perfect for it to work. And then we go and we studied extrasolar planet systems. We found these planet systems with big super Jupiters, super Neptunes, and they weren't in the right place. And how do you get this? And we don't even understand our own planets. So how do we understand hundreds of extrasolar planet systems when we can't even make our own solar system? And so it really is critical to get all the measurements from each of these planets to first of all understand how our solar system formed and then put it in this bigger picture. This little figure on the bottom here is a little bit out of date, but it showed at least as of 2016 how many extrasolar planets we had, and the vast majority start to fall into that Neptune size. So it is kind of an important size class for understanding how those planets form. So let's talk a little bit more about the mysteries. Okay, first of all, how and where did the ice giants form? Did they form farther out than where they are? Did they form closer in? Was it just right they formed where they are? And when did they form? We don't know. Okay, why does Uranus have very little internal energy, assuming that measurement is correct? And particularly if it has the same interior structure to Neptune's. Or again, could you have somehow had an enormous impact big enough to knock it over, reform, while getting rid of all its internal heat at the same time. So that's pretty hard to do. The satellites. Okay, so let's talk about Uranuses versus Neptunes. Uranuses are in equatorial orbit where they belong. They seem to have formed in place with Uranus, somehow over on its side. Neptunes, on the other hand, were captured. They're in orbit in the wrong direction around Neptune. So we think Triton in particular was a captured Kuiper Belt object. So now you've got another big planet out there, and it caught all of its moons. That's pretty different than any of our other planets. So why and how did that happen? The rings. All 4 of our outer planets have rings. But these are very different. So both Uranus and Neptune have dense, clumpy rings. They're different than Saturn's. They're not broad. They're not obvious. You don't see them through a telescope. But they do have rings. Neptunes are segmented. They're not a complete ring around the planet. They tend to have little arcs. Whereas Uranuses are more complete, but they're tenuous. They might extend all the way down to the atmosphere. So there's a lot we don't know about the ring systems. Magnetic fields. Everything about these planets is weird. So they both have complex, off-centered magnetic fields. Our understanding of how magnetic fields form is from that rotating core, usually with a liquid metallic kind of layer around it. They're uniform. You get a nice, like a magnet, a dipole, a north and a south. Well, it turns out on Uranus and Neptune, it's not centered on the center of the planet. It's off to the side. We don't know how you do that. So that's another thing that we're still trying to understand. And it really messes up things with auroras and how the solar wind interacts with it. So let's start with the first one. When and where did the giant planets form? So we've come up with really complicated models on how one forms the solar system. So in this particular version, which is called the Nice model with the Grand Tack, you have each of the planets forming at year 0. They form all around the same time. Well, like all the extrasolar planet systems, Jupiter starts to migrate inward. Now, in a lot of our extrasolar planet systems, the big Jupiters are very close to their parent star. Now, obviously, that's not what happened here, or we wouldn't be here having this discussion. What we've come up with is that Saturn then migrates inward and starts pulling Jupiter back out. Well, at the same time, you have Uranus and Neptune, and they move in and out. They scatter all the stuff in the outer solar system. They kick things out. They grab and capture Kuiper Belt objects as moons, and then everybody lands where it's supposed to be. So that's called the Grand Tack. So we're tacking our boat, we're grabbing Jupiter, dragging it back out where it belongs, and then everything is where it's supposed to be, everything's happy. Well, maybe. Depending on the model, people have run very complicated computer simulations now with many, many, many bodies in them. And in some cases, you have Uranus and Neptune swapping positions. As you know, they're not in the same inclination in the solar system now anyway, so that's completely possible. But there's a very narrow window when you can actually form them and get this particular model to work. So how do you figure out if that's where they actually were? Well, it depends on what you know about the ages of the planets. So we have knowledge of Jupiter, and one of the things you can do is you have to look at the things that don't change. All of our elements in the solar system, some of them get driven off as the planets form, they change over time, they get pulled into different molecules. So what you'd like to do is look at the noble gases. The noble gases don't interact with anything, they don't change. So how much of them you have is very dependent on where you were inside that forming solar system. So for Jupiter, that's great. We had an in situ probe. We measured those noble gases. So it was pretty good. The helium and neon seemed to be a little bit off, so we came up with helium-rene. So if you rene it out, that works out. Okay. Well, what about Saturn? Well, for Saturn to work and be the right age, we have to have a lot of helium-rene, and it takes the neon with it. And this little graph kind of shows you that. What happens is you can figure out how warm the planet is and how old it is. And if you have rain, you can change the temperature. Rain releases heat. So if you release the heat from dropping out the helium and neon, you can make Saturn a little bit older. If you don't do that, Saturn's too young and that whole model doesn't work where it grabs Jupiter. So one of the things we'd like to do is go back to Saturn, actually have a probe, measure the noble gases. And we should find it has a lot less helium and neon. If it does, everybody's happy. But then we have this little narrow window between 4.3 and 4.7 billion years, where we also need Neptune and Uranus to form. So ideally, we'd want to go measure those planets, the noble gases at each one of these planets, and that'll tell us how old they are. The other thing we can do is measure the isotopes in the atmosphere. Just like carbon dating here on Earth, we can do the equivalent with other isotopes on the planets. And those isotopes will tell you where they were in the solar system when they formed. And so really we need measurements directly inside the atmospheres to tell how old they were and where they formed. So, can we get this to work with Uranus and Neptune? First of all, you have to gather up enough material to still form planets, okay? So it can't form too late, or all the material would have been blown out of the solar system. You need them in the right place, the right time, so that everybody can stop Jupiter from sweeping up the inner planets. But you also need them out in the outer solar system at the right time to scatter all the comet and asteroid pieces that hit the Earth during the late heavy bombardment, this period where a lot of things were raining down on the Moon and the Earth. So there's really only that tiny little window where we can get them to form. Okay, well we still have to explain that difference in heat on Uranus versus Neptune. Besides potentially knocking it over, could there be a difference in this helium and neon rain? Maybe it's rained out all of its helium, so it has no more heat left. We don't know. So we still have to rely on that theory where we had the big collision. So what do we know? What do we know about these planets? Okay, for Jupiter, we have all sorts of composition measurements. We have a bunch on the noble gases and the elements. Saturn, not so much. We have a couple of the elements, and that's the stuff that we can measure from outside the atmosphere using a spectrum. We can tell if it's absorbing certain molecules, certain wavelengths, and that'll tell us how much carbon there is, for example. Uranus and Neptune, well, really not good. We can measure carbon, that's about it. So what happens is, because everything is freezing out down farther into the atmosphere, it's not mixing in places where we're going to be able to see it. So the only way to be able to get those measurements on Uranus and Neptune again is to do those in situ, send an atmospheric probe in that directly measures it and tells us what's there. Okay, so let's assume we get our planets to form in the right place at the right time. What about the satellites? Okay, so the satellites of Uranus actually are really very interesting, and I don't think they get the credit they deserve. They're very young, their surfaces, and dynamic. There's a lot of scarps and scrapes on them, Ariel and Miranda, for example. Umbriel has a nice icy polar cap. We don't have a good look at it because we only had that single flyby. We didn't get to look at it from all angles. Titania and Oberon are very icy, but also have quite a bit of impact craters. They might be ocean worlds. And ocean worlds are things like Europa that might have a subsurface ocean beneath the ice. One that's not shown here, just because it wouldn't fit in this scale, is a tiny little moon called Mab. Mab is embedded in Uranus's tenuous outer ring. It might be like Enceladus helping to form that ring. So it's possible that a tiny, tiny moon out at Uranus could be spewing out ice, just like we have for Enceladus at Saturn. Yeah.
Did you say a word about where the names came from?
Good point. So the powers that be, way above my pay grade, decided on themes for each of the planets. And so for Uranus, all the moons are named after Shakespearean characters. So that's why you get Oberon and Titania, Umbriel, and so on. Whereas for the other ones, they have different mythology attached to them.
Okay.
So for Neptune, they tend to be more the sea gods. So you get Triton, things like that. So when we get to Neptune, okay, again, these were captured moons, so they weren't formed in the same place. But even our brief look at Triton, it was a really, really strange moon. It's very big. We have this view of its south pole, and you can see there's dark streaks. Those appear to be plumes. And the prevailing theory is that there's a thin enough atmosphere, you can actually have a bit of wind. And those are nitrogen ice geysers. So extremely cold surface, but it does seem to have some activity. Now the rest of the surface has that funky terrain. It's called cantaloupe terrain because it kind of looks like a cantaloupe. We don't know what that's about. It's actually turns out very similar to what we've seen on Pluto. Now that we have very nice close-up images of Pluto. And so this is what happens when you have ice in certain forms, and you can get a little bit of it to mobilize. But we don't know anything about that other hemisphere at all on Triton. So how many satellites are there on all of these? Lots and lots and lots. They're tiny, they're hard to see. We're still discovering new ones. The one that was just discovered in 2004, the way it works is if you think you found one, you have to find it again. And then you have to find it a third time to prove it's really there. And so until you can plot out that orbit, it doesn't exist. But once you've gotten that, then it gets named, given a provisional designation based on the time, the year of the first observation. So that was 2004, and it just got named this past year. It's Hippocamp. I don't know. But all the other moons are in there too. So we have quite a lot of moons at both Uranus and Neptune. We're still finding more. And as you can see, Triton goes the wrong direction. So what about the rings? The ring systems are very different than what we have at Saturn. So it's a little hard to see in here, but here's the rings of Uranus. There's that faint blue ring. It's very fuzzy up at the top, and they really are somewhat different colors. The red ring is dense but thin, and then there's this whole tiny set of rings that go all the way down to the planet. We don't know where they stop. We don't have a good measurement of where they stop. Neptune's rings, we don't have that tenuous outer ring, and they're very clumpy. You can see the little segments in the top ring there. We actually named the segments because they thought they were permanent. They do seem to come and go. We're not sure how and why you get clumps in a ring. It's a very different system. They do seem to be a bit more shepherded in the Neptune system, so the moons help govern where the rings are and keep them in place. We don't have that on Uranus, and that's part of the reason why the rings seem to be falling all the way down to the surface. Okay, and then the magnetic fields. So this is an exaggeration, but it's the same kind of idea, where you take this bar magnet and you have a north and a south pole. If you look at Uranus, you can see, first of all, it's upside down. And that's this idea that it's kind of past 90 degrees, tilted over a little bit farther. But it's also not centered. Well, for Neptune, it's even worse. It's even farther off center. And so if you can find some reason to form on a moon like a magnetosphere like this on Uranus, okay, maybe it got collision, got knocked over, it messed up the magnetic field. Well, how do you explain Neptune then? It's even farther off the center. So we're not really sure how that happens. One way you could do this, of course, would be the fact that it's not down in the core that the magnetic field is forming. It's a little bit farther out, but you still need it off to one side, and that's the part that's really hard to explain. Now, to do a magnetic field measurement, you really want to be able to fly over from multiple sides, multiple directions. And in particular, if we think there's some mass reason, maybe somehow the interior of these planets is lumpy, or has, a concentration, like the moon has mass concentrations, you need to have lots of close gravity passes. And we only had that single flyby, and in the case of Neptune, it was equatorial. You really want a polar pass too. Then you can map out that whole magnetic field in much more detail. So we're still trying to understand how you form these off-center magnetic fields. So what can we do remotely? So we don't have a mission there. What can we do from here? So the best thing, of course, would be to have lots of space telescopes. Don't have the Earth's atmosphere, don't have cloudy nights. Preferably in permanent orbit. They don't have any problems. They keep working. Where you can take lots and lots and lots of rapid measurements. Just keep watching these planets. That would be this great thing we could do. You could learn a lot about the dynamics, how the clouds change, how the winds change, possibly a bit about the interior. You can also do some really interesting experiments that I'll show you in a minute to learn about the deep structure. And it's basically doing seismology from far away. So that's one thing we'd like to do. But we don't have that. So we can do periodic lower spatial resolution observations from Earth. So that's using ground-based telescopes and things like Hubble. Now, unfortunately, Hubble is not a planetary telescope. They don't just let me use it all the time. So we do have to compete with everybody else. So we don't get as much observations as we'd like. We can still measure the cloud top winds. We can watch storms. One thing we can do really well for the ice giants is using adaptive optics. We can observe them in the infrared. So the Keck telescope Gemini, all those get used quite a lot, and they can do spectacular imaging. There's some limits to what they can do in the infrared, but we can get a lot of data from them. We can get some composition chemistry if we have high-resolution spectroscopy. So basically taking a spectrum, we can do that. We can get some of the, mostly carbon, but we can't get those noble gases. We can also study the atmospheric and ring structure from stellar occultations. So if a star passes behind the planet and we watch it, we can learn quite a lot. This is hard to do when we're talking about very close to the planet because it tends to be bright, so it's hard to watch the star come in all the way, but that is something we can do. But here's the caveat on this. A lot of this only works because we know something about them already. So when we do this for extrasolar planets where we don't know anything about that planet, it's really hard to do this and figure out what's going on. So if I took a spectrum of Jupiter or Saturn or any of these planets, you wouldn't know that they're mostly made of hydrogen. You would think they're mostly made of methane and ammonia because that's what I can see in a spectrum. So you have to be a little careful with these techniques, and like I said, they work very well for us because we have had these missions and we know more about them. So let's talk about that first one there, long duration high cadence observations. So we can do something that's the equivalent to seismology, and this was actually discovered with stars. We can look at the Doppler signal of a planet, okay, and what happens is anything going on in its interior will basically ring through the whole atmosphere. So it's just like an earthquake here on Earth where we use that fault slip or whatever else to measure what's going on in the subsurface of the Earth. We can do the same thing on how these waves propagate. So whether or not you have a core versus a shell, all these things you can figure out if you can see that ringing. So this is readily observed in the sun. We've actually seen it in the sun and other stars. And in the planetary atmosphere, you don't have an earthquake, but you can actually get those big, strong storms to do the same thing. So that's the theory behind it. Should work. Does it? So this is highly experimental. This was tried first on Jupiter. And using some spectra, they got one detection of what are acoustic modes in Jupiter. So that was a pretty good proof of concept. For Saturn, we haven't been able to do that on the planet yet, in part because the rings are in the way. But because Cassini was there, we actually could watch oscillations move through the rings of Saturn. And that's happening because the planet itself is oscillating and causing the gravity field to oscillate, making the rings oscillate. So it does work, but it's a very difficult measurement. So can you do this on Neptune and Uranus? Well, we did a little experiment where we used the Kepler Space Telescope to observe Neptune first. So Kepler is designed to look at exoplanets, so it's very high precision over long periods of time. And so what we did is we let Neptune cross the field of view of Kepler and bounce around, turn around. We got 90 days of observations with 1 minute cadence. So every single minute we had another data point. What does that look like? Looks like that. And you can see there's some periodic stuff going on in there. And so what we were hoping to do was be able to get to the point where we could actually see Neptune oscillating over time. So what is oscillating in that curve right there? It's not Neptune. You can take that light curve and do a Fourier transform on it to get out what the signal is. And what happens? First thing you get are the known cloud features marked in blue. So that's the most of what you're seeing in that right there. You're seeing the clouds as the planet rotates. Turns out if you get down to the next level, we can actually see the sun oscillating in reflection off of Neptune. So that's how good that telescope is. Unfortunately, we could not quite get to the level where we could see Neptune oscillating. We would have had to get even slightly better with noise. And because Neptune was moving across the Kepler field of view from one pixel to the next pixel to the next pixel, the difference from pixel to pixel dominated, so we couldn't quite get to Neptune oscillating. But we could see the clouds and the sun oscillating. So what was interesting about this was, if you look at those rotation rates, none of them match Neptune's rotation rate. And so what happens is the clouds are moving at the wind speed, not Neptune speed. And so if you did this on another planet, you wouldn't actually get the planetary rotation, you would get the wind field. So it was still very interesting. We actually had Hubble light curves at the same time, so we could show the Kepler folks exactly what clouds were in the image at the time because they were not resolved. So it was a really neat experiment. It worked very well. We've done this twice more now, once more on Neptune and once more on Uranus. We're still reducing those data, so we're still hoping to get the oscillations out. But just to even get to the point where we could see the sun oscillating in reflection was a very cool result. So how does that compare to lower cadence data? On the left here we have Spitzer-like curves that we took at the same time as we did those Hubble ones. It turns out that in the infrared, because those planets have such different atmospheres, particularly Neptune, where you don't have a lot of haze or cloud, there's not a lot of reflection, it actually has huge variations in the infrared because those clouds really stand out. The whole planet goes black and the clouds stand out. So we see a lot of variation in there. Spitzer is in its warm mode. It's not super sensitive right now, but it at least shows there's something comparable. We typically do imaging in the infrared instead. On the right is our Hubble data that we took at the same time. One thing you'll note is, again, in the infrared you can see bright clouds. You can't see great dark spots in the infrared. You need visible wavelengths to do that. And that's because it tends to be dark at blue wavelengths only. So you can't see any great dark spots, you can just see bright clouds. So the only thing we can do for Neptune really is Hubble to get that. And so that's the images I showed at the beginning. We've been monitoring now every single year with Hubble since 2014. So we can look at changes over time for Uranus in particular in those little storms we see near the pole and of course the polar haze. And then for Neptune in these other clouds and dark spots. So Uranus, that's 2014 and 2019 on there, so fresh data from last fall. Uranus has really, really gotten much brighter. So it passed equinox in 2007. It's been about 10 years now, 12 years. And that polar haze is basically building up as the pole is looking at the sun. So you're getting more and more hydrocarbon smog on Uranus, essentially. And so we've been watching that build up over time. And it's not just sunlight, it's also dynamics in the atmosphere, how the circulation changes with the season that's causing that to build up. So that's actually been a lot of fun. And then there's these other persistent little storms that are near that polar cap, and those kind of flare up and then die down a little bit, but they haven't gone away. So we are seeing storms on Uranus as well. If you do this from ground base with Keck, again, we've been watching it as it went past equinox, and you see that same thing with the polar haze brightening. We have seen some storms pop up. In particular, we were looking near equinox because we thought as it changed seasons, you might then suddenly see all these storms popped up. And at equinox, nothing happened. But in the years after there, it's actually gotten quite active. So there is a seasonal lag there. We've also done spectroscopy on Uranus. And we detected that hydrogen sulfide in the atmosphere. We expected it to be there, but it's difficult to measure. There was also Herschel data, which was very interesting. They were looking at stratospheric carbon monoxide, and they determined that the source of it is external. It's not in the atmosphere, it's raining in. And it was more consistent with comets than with just rings falling in. So that's another very interesting result. So there actually has been a lot of work on Uranus in the last few years. We also had Neptune. So when we started the Outer Planets program with Hubble, we started it in 2014 with Uranus, and then 2015 we picked up with Neptune. First thing we saw was a great dark spot. It wasn't that great, it was kind of small. But it was there, and it was sitting in southern latitudes, similar to where we saw the Voyager great dark spot. And over the next couple of years, we watched it drift a little bit towards the pole and just disappear. So about 3 years, and it was gone. When we looked in 2018, actually we were looking for the little guy. It was gone. We had a brand new big one up in the northern hemisphere that was the size of the Voyager great dark spot. And so we were able to go back, because we had a couple years of data, and look at our maps from each year. And it's a little hard to see with the contrast in here, but we actually found clouds where that storm was before it became a great dark spot. So now we could track it back and know that it took about 2-3 years for that storm to form. So it's clearly something happening deeper in the atmosphere that eventually becomes this nice dark spot. So that was quite interesting. Now Neptune's nice and ground-based. You can actually get pretty spectacular ground-based data from Keck on Neptune. Again, you can't see those great dark spots, but we can watch quite a bit of the cloud structure.
Is that not visible?
That's in the infrared. And that's only because you can do the adaptive optics in the infrared. There is adaptive optics now on one telescope in, I think it's the Canary Islands, in the visible. And they have, once they got a very good, nice, sharp Neptune image, but it's really a struggle in the visible wavelengths. So we tried again, actually, to get this new great dark spot with the ground-based AO in the visible, and it didn't work.
Which infrared band is this?
This one's probably H band, I think. It's H or K. Okay, so let's talk a little bit about when do we get to go back there? So we've been working on this a lot in the last few years about these planets really are so important and so interesting. What can we do to get back there? And so just a couple of years ago, we completed a big engineering study looking at all the possible mission options to these planets. So a flyby of Uranus, or a flyby of Neptune, or an orbiter with or without atmospheric probes, everything you can think of. And the idea was to kind of get an idea of the full trade space, how much would it cost, how hard is it to do. The recommendation, of course, is that the best mission is to get into orbit, have an atmospheric probe, you know, all the bells and whistles. But it's really, really challenging to get out there. So these planets are far away. We had to look at how long can your spacecraft reliably last. So we know the Cassini spacecraft lasted for almost 2 decades, but it wasn't built for 2 decades. It was only built for 4 years. And so if we had run that same mission scenario on that spacecraft, they would have said, it won't last 2 decades, it's not built for that. So we know they typically last longer, but we still have to go by those rules. So we wanted our missions to go from launch to end of mission in less than 14 years. So, okay, that's reasonable, except when it takes 12 years to get out there. So the best thing to do is to use a Jupiter gravity assist. Our friend Jupiter is helpful there. So to do that, you really want to launch towards the end of this decade or into early 2030s. After that, you lose Jupiter again for another 10 years. So that's what we're kind of looking at as a timeline. The other alternative is to get one of these mega launch vehicles that doesn't exist yet, but then you can really cut your flight time down.
What about ions?
Again, if we can get to those fancy things, we did require the solar electric propulsion on Neptune to get there anyway. Uranus, you can do chemical. So we followed this up, and of course, there's been a lot more interest in this now. So the European Space Agency, ESA, has also gotten quite interested. So they also have completed several studies. First, they were looking at what they could best do to contribute to a NASA mission, which requires a lot of cooperation and agreements, of course. But they looked at either doing one of the atmospheric probes, doing a Triton lander, or doing the second spacecraft. Why can't we launch to both? Have 2 spacecraft, 1 huge launch vehicle, launch to both. So we looked at those options. It's difficult to fit 2 big spacecraft in a launch vehicle. And it does require the SLS, which we don't have yet. They also looked at, instead, let's do separate launches, but do them close together in time. And that works as well. So there's a lot of interest in doing this right now, and we're still continuing the engineering studies and working on that. But there's also been several grassroots ideas where people have come up with other ways to do this. One option is to do an ice giant / Kuiper belt mission. And this of course is popular with folks because of the Pluto mission as well. And the idea is that you do your Neptune orbiter as your big ice giant mission, and you do a Uranus flyby on the way out to the Kuiper belt as a smaller mission. And so that's one way to do it. They keep all your communities happy, and all the scientists get their targets, and you have one expensive mission and one that's a bit cheaper rather than 2 mega missions. But folks have also looked at how you could do small, cheap things to either enhance the mission or be the mission. One idea is to do secondary atmospheric probes, so have very small, cheap atmospheric probes and do more than one. So the reason that this is good is that for those of you who remember the Galileo mission, we had our atmospheric probe. It was really nice. It went into a bad spot. So we tried to measure the clouds. We didn't find any clouds on big cloudy Jupiter because we went into a hole. And you know, it's how life works. I don't know what to say. It was a choice of location, but also the fact you only had that one shot. Whereas if we had a second probe in a different latitude, we wouldn't have had that problem.
What do you mean by going into a hole?
Literally, it was a hole in the clouds. So we went straight through the atmosphere trying to measure all the clouds. We never found clouds because Jupiter at that one latitude has a big wave, and you get big clouds and big holes. And you had a 50-50 chance of going into one or the other. Now, we can argue about why they picked that latitude, but that's for another day, I think. So you want to avoid that, if you can. And the best way to do it, of course, to avoid going into a unique spot is to have more than one spot. So that would be nice. It gives you also more information about global things. Is that latitude different from another latitude? You can't tell that from one probe. There's also a proposed mission right now in competition to do a flyby Triton with one of the smaller class missions. And then there's a Neptune orbiter and Triton lander under study right now as a bigger mission. So there's quite a lot of missions out there, and all I can say is, let's go. So to just kind of wrap up, the ice giants are really interesting systems in every possible way. They have interesting moons, they have different atmospheres, crazy magnetospheres, interesting rings. We need to have a big mission to one of these planets to truly understand how the ice giants work. Thank you.
Yeah, I'm curious a little bit about the history of humans' exploration or really discovery of these planets. I think I read somewhere that Galileo was the first one to see Neptune. Is that correct?
I don't think it was, no, was it Herschel?
No, I thought he saw it, but he didn't know what he was looking
That
at.
maybe, I'm not sure.
It was apparently right next to the other planet he was looking to at one point when he looked at it. So
Okay.
they very well have seen it, but they didn't realize what it
Didn't
was.
recognize
Yeah, that's
Okay.
what I heard
Okay.
as
But
well.
yeah,
I read somewhere just recently, reading the magazine, they're casting doubt on the late heavy bombardment theory. Can you talk about that a little bit?
So, again, there's a lot of problem with these solar system models and what actually happened. So we're trying to basically do forensics on the planets based on what we can see now. So you're looking at crater counts and trying to figure out when those craters happened, which leads to late heavy bombardment. Some people say that those ages and counts aren't right. These very complicated models. Some of them have Jupiter and Saturn jumping each other. All sorts of things have to go on to get our solar system where it is now. And I think as we learn more, each of the models evolves. And they've gotten rather complicated. It's not an Occam's razor at this point. Doesn't mean it's right or wrong. It's just that we're looking at an enormous game of cosmic billiards. And we have all these particles and all these bodies all over the place. And they all interacted, right, to get where we are now.
That's what I call the planetary ping pong.
Exactly.
When you said that it's rain-released heat, are you talking about really upper-level mechanical transition to rain, and that's the release of the heat? Is that the dynamic you're talking about?
The release of potential energy as it condenses and falls.
As it condenses, so it's a mechanical, but it's really upper level.
While it's falling down into the interior, it's not up in the weather layer, it's deeper than that, but it is still pretty high up.
So I don't understand the convection, how you conduct that out.
Well,
Like it's out.
it does depend how far down they go and they settle, but it is complicated, and the neon dissolves in the helium, and then they fall down together. So it's a complicated process to get it to work.
So if I were to go up in that atmosphere, then I would see a raise in temperature as a result of that process as it's occurring, and there's radiation from that layer.
Right, and
Okay.
we do see temperature inversions in all the planets. The temperature profiles are not super well known. The very highest parts of the atmosphere are from occultations, but lower down are not.
Okay, thank you.
So the question about the late heavy bombardment is concerned because it's dependent, as I understood that article, on one measurement from the moon. My real question is there a real incentive to go back to the moon and study the moon for purposes of understanding the solar dynamics, the solar system dynamic.
Yeah, I think for a while there was not quite as much interest in it. It's kind of gotten some renewed interest, in part because there's also potential for humans to go back to the moon, but we still have lunar measurements going on through a variety of spacecraft. I think what you find is it depends who you talk to in the scientific community, because people tend to be somewhat narrowly focused by target, which is just how it is. But, you know, I think in general, you want measurements at a lot of different bodies. And that's kind of the problem, is we're trying to piece together a solar system, and we look at one object, one measurement, one body, you don't get a full picture. And so there's a lot of things that go on when we're trying to understand how this all works together. And, you know, you would never take one measurement of anything, ever, and assume that was perfectly the answer. You know, you don't fit a line to one point. And then we keep trying to do it.
So if you're a salesperson wanting to send these expensive craft out to these Neptune and Uranus, what's the selling point? What is it that you're saying, hey, we got to do this because?
Part of it's that innate wanting to understand how we got to be here, right? How did the Earth form, and how did it get the right conditions for life? Why are we the only ones that have these conditions, as far as we know? You know, it's this understanding of the origins of life.
You know, I was wondering about, I've heard a lot about Neptune's super fast winds. In fact, it's down at, you know, close to 40 or 50 Kelvin. Usually it's the difference in temperatures that drive these fast winds. It almost seems like it's counterintuitive to say that supersonic winds. Is that possible that without having the chance to have it close enough to the sun to produce uneven heating?
Right, and that's part of our problem in trying to understand what's going on in these planets, is that it's clearly not a solar influence. Part of it's the internal heat, part of it's the rapid rotation. These planets rotate, you know, 10, 20 hours. For a big body, that's pretty darn fast. So that's generating some of this, because it is a fluid atmosphere. But you're right, we're talking 900 mile per hour winds on a body that's, you know, 60 Kelvin. It's very hard to understand how you generate that.
I have a question. Are there any speculations about the off-center magnetic fields?
I haven't heard any, actually, that I'm not real tied into the magnetosphere community, but I haven't heard a good explanation, anyway, for how to do that.
If the core is offset, wouldn't that be part of it?
Well, the core is always going to be the center, the core itself. It would have to be more these shells and the dynamo itself, and why it would be pushed to one side is hard to explain.
It's a higher order magnetic monopole. The Earth's magnetic axis is offset from the spin axis by about 400 kilometers.
Can you describe a little bit more what an icy atmosphere is like?
I wish I could. I mean, people have asked me what would it be like to if you were floating in the atmosphere of any of these planets. And you know, I think, again, they're all fluid. It's going to be, in some parts of it, it'll be much more gaseous, and others it'll be more fluidy or slushy. And in these cases, because they are so cold, probably a little more slushy.
Would you be able to look at these plans with the James Webb telescope when it goes up?
Absolutely. And actually, Uranus and Neptune will be quite good with JWST, because it's an infrared telescope, so we'll be able to see these clouds and a lot of structure. But the biggest problem we have with James Webb is it's not built for planets. It can track moving objects, but it's a little bit of a challenge, and it's also not designed to do the one thing we like to do with planetary, and look at opposition. You can only look at quadrature, so you have to look off to the side. And there's a huge tax to turn it because it's such a big spacecraft. So to flip it all the way over and look the other way is going to be problematic. So it's going to have limited time windows when it can look at the planets.
Yeah. Because of their size, isn't the gravity on these planets pretty extraordinary, pretty high? So I can't imagine floating in the, without being crushed.
Active floating.
Yeah.
On the upper atmosphere, the pressure is no different than here. The cloud
Oh.
layers typically have 1 bar, some atmospheric pressure here.
Oh,
It's
okay.
when you go down, so atmospheric probes get crushed pretty quickly.
Okay.
There was some, oh,
Why have we learned recently that we might, from these two planets, that we might extrapolate further out to other Kuiper belt objects and structure the solar system further out?
Well, for the Kuiper belt object, not as much now because we haven't had really high resolution data for something like Triton. What we're still trying to understand is again where they were, how much influence they had on scattering things in the Kuiper belts. But again, until we can get some in situ measurements, it's going to be hard to do too much more with those.
over there, yeah.
Yeah, a couple of questions. One, is there any interest in mission focusing on Miranda?
Yeah.
The second question, on that design you showed for a Uranus and Neptune orbiter, there were obviously huge fuel tanks. I'm wondering why the hell would you put huge fuel tanks on? Because the only sensible reason to get an orbiter and these outer planets is to aerobrake, and then you don't need much fuel.
Actually, you can't aerobrake. We've looked at aero capture, which is just slowing down through the atmosphere, and it doesn't buy you as much as you think. Part of the big tanks is getting away from Earth and the deep space maneuvers you need to line up. What we end up having to do on a lot of these is a Venus, Earth, 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 Venus, whatever, Jupiter, flybys to get out there. It is fairly complicated.
Capture, though, it seems like the obvious thing to do to avoid a huge amount of fuel.
Well, because you're going awfully fast for one thing, so to not just skip right through is difficult. The technology is also a little bit questionable. We haven't tested it at those levels yet, but by the time you've done everything to get out there, it didn't buy you that much, it turns out. So a lot of that fuel tanks really isn't just to stop. A lot of it is getting out there.
If there are no further questions, let's thank our speaker again.